Let's now use this gray approximation to find the Eddington solution, which is an ingenious solution to the gray case in the plane parallel approximation presented by Arthur Eddington. So Eddington assumed that the intensity could be decomposed into a contribution coming from two directions. He assumed that in the plane parallel atmosphere, you only had rays going up or down. So this is the plane parallel atmosphere. You have the intensity going up, let's call it I plus, and the intensity going down, which is I minus. Basically, these are the only two directions that you can have in a plane parallel atmosphere. In spherical coordinates, that would be equivalent to this geometry. In any radius, you only have an intensity going up and an intensity going down. And you label I plus the intensity that is directed outwards. That means from the stellar interior towards the surface. And I minus would be the intensity that is directed inwards, going from the surface to the interior. So in terms of, again, spherical coordinates, the intensity field is I plus going outwards. That means for meridional angles going from 0 to pi over 2. And I minus, that's the one directed inwards for meridional angles going from pi over 2 to pi. Remember that spherical coordinates are defined going from the meridian. If you define this axis as being the z-axis, that means that the meridional angle is defined as this angle in here. So you have then from 0 to pi over 2, that's the intensity being directed upwards. And then from pi over 2 to pi, you have the intensity being directed downwards. And for both cases, the azimuthal angle goes from 0 to 2 pi. So we can express the mean intensity, the flux and the pressure in terms of this intensity field. In the end, what the Eddington solution is going to give us is how the temperature depends on the depth. But let's look at the steps along the way to arrive at this result. So the mean intensity is the directional integral of the intensity field. So if you plug in this definition of the intensity, so this becomes 1 over 4 pi times the integral in the azimuthal angle. And now we split the integral in the meridional direction from 0 to pi over 2, that's the I plus, and from pi over 2 to pi, that's the integral of I minus. So this integral gives you obviously 2 pi. It's going to cut to this 4 pi to give you a half. And if I plus and I minus are constants, you can take them out of the integral. And these half integrals of the sign give you each one of them equal to 1. So the mean intensity then becomes half of I plus I minus, which is intuitively what you would expect anyway, right? The mean intensity is the directional integral. You have one ray that is going up, we have another ray that is going down. The mean intensity is the average of these two intensities. And now for the flux. The flux is the integral of I times the cosine of theta in direction. So play the same game. The flux now is integral of 0 to 2 pi of the phi. And now break the integrals in the meridional direction. Again, in a positive integral for I plus from 0 to 2 pi of sine theta cosine theta. And an integral in I minus, also of sine theta and cosine theta, but from pi over 2 to pi. So these integrals here, this gives you half, and this gives you minus half. The flux then becomes pi times I plus minus I minus. Again, this is an intuitive result. The flux is a vectorial quantity. So if you have an intensity going up and an intensity going down, unlike the mean intensity, which is a scalar quantity, is the average of these quantities, the flux cares about the direction that they're going. So the one that is directed inwards is going to subtract from the intensity that is going outwards. And then you have that the flux that you measure is going to be one minus the other. Notice that if you are in an isotropic field and I plus is equal to I minus, then you have that the flux is equal to 0. as we would expect for the center of an isotropic field. As for the pressure is 1 over c times the directional integral of the intensity times the cosine square of theta. So this is going to break into 2 pi over c times the sum of these integrals. Now, this integral here depends on the cosine square. So as you can imagine, that's going to give you an even function with the angles. It's going to be a plus, not a minus in the sum of the integrals. Indeed, these integrals both give you a third. So what you have then is equal to 2 pi over 3 over the light speed times the sum of the plus intensity and the minus intensity. You can substitute that actually for the mean intensity, and it gives then that the pressure is equal to 4 pi over 2c times the mean intensity. Okay, so this is the solution for the Eddington atmosphere in terms of the mean intensity, the flux, and the pressure.